Okay, we'll try not to have you fall asleep. Okay, why don't we get started? So next Tuesday, there will be another quiz, and it will just cover basically the optoelectronic diodes. Just qualitatively, you should know how those optoelectronic diodes work, and then the MOS capacitor. Okay, so hopefully it won't be too much. You're going to be able to add one more page of handwritten or typed up notes, and again, should be no need for calculators on the quiz. Okay. Okay. Were there any questions left over from the last lecture, where we talked about the MOS capacitor charge distributions and small signal capacitance? Okay. All right. So today's lecture, we're just going to focus on non-idealities in an MOS capacitor structure. So what are some realistic things that show up when you measure a real MOS device? And then next time we'll start on talking about the transistor. Okay. Okay, so the first thing that's non-ideal about an MOS device is that there is always going to be some electronic charge somewhere within the oxide. And historically, the reason why MOS transistors were demonstrated well after they were the concept was invented is because of oxide charges. So an MOS transistor compared to a junction transistor, bipolar junction transistor, needs a insulating material on the surface of the semiconductor. And it turns out that if there are charges in the oxide, then they can actually greatly affect the threshold voltage. Okay, so in an MOS device, usually you'd like to be able to bias it between accumulation and depletion and inversion. But if the threshold voltage and the flat band voltage are shifting all over the place, then you really can't get a reliably working device. So if you look at this schematic cross-section of an MOS structure, you'll see that there are these mobile ion charges in the gate oxide layer. So those were the kinds of things that practically existed in the early or late, mid 1900s. Okay, people didn't realize that ions such as sodium and potassium can easily move around in silicon dioxide and basically affect the charge that's in the silicon underneath. And so this is why the threshold voltage was really hard to control in early experiments. Okay, so where does sodium and potassium come from? Just curious. Action process. Okay, yeah, that's fine. But Andrew, did you have some? Yeah, so from us, basically our sweat and all that, basically we're a good source of sodium. So people didn't realize that we had to avoid touching the surfaces of things that touch the surface of wafers. So cleanliness was not on the top of everybody's minds. If you saw the pictures of historical pictures of the first transistors, people are, just there's like no clean room or anything. So that's fundamentally why it was just difficult to make any MOS transistors reliably. So we'll talk about that in detail. Also, at the interface between perfectly crystalline silicon and the silicon dioxide is actually amorphous. Okay, so it has no regular lattice structure. And so it's not going to have any regular bonding structure between the silicon and oxygen atoms. And that's also the case at the interface between silicon, single crystalline silicon, and amorphous oxide. So there basically will be dangling bonds at this silicon and oxide interface. And so basically you have silicon atoms, and suddenly there's no more silicon on top of it, but you have this amorphous material. So some of those silicon atoms, they would like to form four covalent bonds, but some of those bonds are not going to be satisfied, to have 2 electrons. So you have some dangling bonds at the interface, and if an electron wanders around, that dangling bond can trap an electron. And electrons represents charge. So you can actually trap charge at the interface between silicon and silicon dioxide because of these dangling silicon bonds. Also, inherently, with the silicon dioxide system, there's always going to be some net positive charge right at the interface. And that also affects the threshold voltage of your MOS device. Okay, so just to summarize, we're going to go through every one of these. There's going to be one slide on each of these 4 types of charge. You can have mobile charge moving around within the oxide. You can have trap charge in the oxide as well that doesn't move around as you apply a voltage to attract or repel it. And then at the interface, you can have fixed charge that doesn't change with the applied voltage, but you can also have interface trap charge that does depend on the bias voltage. So so this depends on voltage, and mobile charge actually also depends because when you apply a gate voltage, that means you're inducing an electric field across the oxide, within the oxide, and that electric field will exert force on any charged particle and cause those mobile ions to move around over time. Okay, so let's go over every single one of those, but let's figure out first, just in general, any type of charge in the oxide or at the oxide silicon interface will essentially shift your threshold voltage. Okay? So the general equation that you can use is given here on this slide. The change in the threshold voltage of your MOS capacitor or MOS transistor is given by this equation. So this coordinate system looks like this. So here you have metal, and you have oxide, and you have semiconductor. And we're talking about X equals 0 at the top surface of the oxide. And so X equals X naught, the thickness of the oxide at the oxide semiconductor surface. Okay? So maybe, hopefully it's not, qualitatively, hopefully this doesn't, it's not too confusing. So this rho sub ox is the oxide charge density. So it's in coulombs per centimeter cube of the units. So if you have positive charge density, if you have some positive charge density in the oxide, let's think about an NMOS device. Okay, so let's say you have a P-type substrate, P-type silicon substrate. You have some silicon dioxide over that P-type silicon substrate and a metal gate on top. Okay, so if you have positive charge somehow, just let's say it's existing within the oxide, do you think that positive charge will make it harder or easier to invert the type of the P-type substrate? In other words, to push away or drive away holes, the form of depletion region, and to attract mobile electrons to the surface? Do you think you'll need more or less gate voltage to invert the surface from P-type to N-type? Less, right? It'll be easier. If you have positive charge in the gate or oxide, it'll be easier to invert the surface. In other words, you'll decrease the threshold voltage, right? So that's why this delta VT due to oxide charge is negative, right? You're just making it easier to invert the surface. It's the same case if you have a N-type semiconductor. If you have an N-type semiconductor, and let's say you again have positive charge somehow in the oxide, okay, now to invert the surface, you have to drive away the mobile majority carriers, electrons. So you leave behind positive ionized dopants. And then you want to attract mobile holes to the surface to invert the surface to become P-type. Okay, so does it become easier or harder to invert the surface if you have positive charge in the oxide in this case? Harder. But that means you have to apply even more negative gate voltage to invert the surface, right? So this shift in VT is the same sign, no matter if it's N-type or P-type silicon. Did you have a question, Ali? Okay, so your question is, why don't the oxide charges go into the silicon? Okay, that's a good question. So let's see. So potassium and sodium, why don't they just go into the silicon? Okay, so the easier question to ask, okay, so like if electrons get trapped due to dangling bonds at the oxide interface, why don't those electrons just go into the oxide? Well, there's a big potential barrier, right? The 3.1 EV kind of potential barrier for electrons. Okay, so in the oxide, there's a huge energy band gap. So technically, that means no. Oh, okay. So that's a good question. Okay, so energetically. Okay, so the question is, okay, so these charges that are in the oxide are not in the conduction band. Yeah. So, and they're not in the valence band either. They're basically. All right, let me sketch the energy band diagram. It's a good question. So let me just sketch the energy band diagram for this MOS capacitor. Let's see, which way do we want to do it? Let's sketch it like oxide. And like let's just say the surface is is p-type silicon and the surface is slightly depleted, like this. So this is silicon. This is silicon, and here's the silicon dioxide. Okay, so where do these charges exist energetically in this energy band diagram? Okay, so for this trapped charge here, they actually exist sort of within the energy band gap. Okay, for this mobile, okay, so for the oxide trapped charge here, generally they're somewhere up here. Okay, so this would be like trapped charges. So the trapped charge, okay, so oxide trapped charge usually is associated with a defect in the oxide. So what's the defect? It's amorphous, okay. So what it means is like an oxygen vacancy. So instead of SiO2, it's locally like Si rich or something. So you're like, typically you can form an oxide with like locally an oxygen vacancy. So typically these allowed energy states associated with a vacancy defect are closer to the conduction band edge than the valence band edge in the silicon dioxide. But bottom line is, okay, so this, put it in a different color. This distance here is usually about 1 electron volt. So it's still pretty long distance, so the electrons are not going to jump up into the conduction band and move around. Okay, so that's why they're not mobile. And so the ions, I think that is a similar situation. It's just that they're physically mobile, right? So energy-wise. Oh, the ions, they're atoms, right? They're atoms of potassium and sodium moving around in the oxide. So basically, energetically, they're somewhere in the band gap, but they're just, so the charge is not going to, like, it's not like you're going to contribute an electron or a hole to the oxide. It's just physically some charged particle moving around in the oxide. Yeah. Oh, okay, so the question is, why don't you just have these electrons tunneling through? Okay, good question. Okay, so the question is, well, typically this oxide thickness nowadays in modern devices is less than 5 nanometers, just a couple of nanometers. So isn't it easy for electrons to just quantum mechanically tunnel into or out of the silicon? And indeed, that's what happens. So, okay, so this is an advanced topic. You can people will cover it maybe in a graduate level class. But what happens then is, let's say you have an inversion layer formed in the, like for p-type silicon, an inversion layer of electrons formed at the surface. Okay, what can happen is, yes, the electrons can actually tunnel quantum mechanically into the oxide, and occupy one of these vacancy states. But they can easily tunnel out. Okay, so what happens is then you actually have electrons that tunnel in and out, and that leads to time, over time you have variations in the inversion charge density with time. And that actually leads to variations in the MOSFET current, because now this inversion charge density is going to be a function of time. Okay, so what happens is then, if you plot the current flowing in a transistor from the source to the drain, and you just apply gate voltage and a source drain voltage, and you measure the current, you see it like changing with time, okay? Because of this trapping and detrapping of carriers. So in reality, yes, that does happen, and that leads to what we call random telegraph noise. So noise is actually a practical problem in designing low voltage circuits today. Right? Yes, Andrew.
When you're like actually making a MOSFET, are there cases where you
That's a great question. Okay, so the question is, do we ever purposely want these charges in the oxide? Ordinarily, if this is the MOS capacitor, like in a transistor, normally, no, you don't want these oxide charges purposely introduced in there. Certainly if it's mobile, because then over time, let's say if you turn on a transistor by applying a gate voltage, then over time these things will move up. And if you look at this equation, depending on the position of this charge, right? So basically this equation is kind of weighting. So X increases as you go closer to the semiconductor. So basically the charge density that is closest to the semiconductor will have more influence on the threshold voltage than charge, let's say if we have a charge distribution here versus a charge distribution here, this charge here will have larger magnitude of impact on the threshold voltage. So if the charge is moving over time because you're applying a gate voltage, then this means your threshold voltage is changing over time. That's undesirable in general. There is, so this topic of research is that, okay, so the question is, would you ever want this purposely? So let me just give you a simple example where it might be in the future desired purposely, is that, let's see. Yeah, okay. So this was actually done a long time ago, but it turns out when we talk about the transistors next week that if you want to make a transistor very small, if you want to make the gate length really short, so let's say this is the gate, and you want to make it really short laterally, that means you want to form very, very shallow doped regions next to it, right? Basically, if you want to scale the lateral dimensions of a transistor, it turns out, we'll cover this in a couple weeks, you actually want to scale the vertical dimensions as well. So technologically, it's not trivial to make such a shallow junction. It's very difficult to make these junctions less than 6 nanometers in depth. So what people have done in the past is that, well, we've done, this is just research, is we actually just implant purposely some ions. Turns out cesium is not bad for this. So cesium is a larger atom than potassium and sodium, so it doesn't really move around too much in the oxide, but it has a positive charge. So then we can actually just implant some oxide charge, purposely put lots of charge in the oxide to induce an inversion layer up here. So that sort of acts as a very shallow source drain conductive layer, right? But that's still research. Nobody's doing that in production, I don't think, yet. Okay. But so in general, no, we don't want to purposely introduce charges in the oxide. Okay. Because usually you do that by implanting, and that might damage the oxide, so it actually doesn't act as a good insulator. Okay. Okay. Great. Good questions. So bottom line is you just used a simple equation to determine what the influence of oxide charge is on the threshold voltage. Okay. So that's a major effect of oxide charge. But also, Coulombic scattering. So the influence of charge in the oxide can actually affect. It can introduce cause carriers Like if there are electrons flowing from one direction, like across the interface, or along the interface, they can actually be exert, and they can feel a coulombic force due to the charge in the oxide. So then they can be scattered more. So they can effectively reduce the mobility of electrons, let's say, moving along the surface between, let's say, N plus source and drain regions, right? So if you want an electron moving very quickly along the interface, you really don't want it to exert, to be under the influence of more scattering, due to coulombic charge. Okay? Okay, so this is just the general equation. Fixed oxide, so let's go through the 4 types of oxide charge. The fixed oxide charge is always going to be located right at the silicon dioxide interface. Okay, so it's located at x equals x naught. Okay, so it turns out then that is very simple. The influence of the fixed oxide charge is given by, okay, so basically there's going to be some shift in the threshold voltage, and that's going to be equal to some Q, okay, from Q over C, right? It's a MOS capacitor, so Q equals CV. So that means any change in the voltage is going to be due to the change in the Q, the charge in the semiconductor, divided by the oxide capacitance. So this QF is just sort of non-ideal. So that's going to be, so you just have a simple equation like this. Except it's negative, right? Because QF is greater than 0. Okay, so at the oxide interface, you have some charge. So that means that, let's just draw it here. Just energetically, it might not actually be there, but anyway, there's some charge, positive charge at the silicon dioxide interface, and that's going to result in some built-in electric field, pointing to the left. So I'm just drawing that because remember, if there's an electric field present, then there's going to be band bending, right? So this is why you have band bending in the oxide in this direction, right? Because of that electric field induced by the fixed oxide charge. Okay, so typically QF is about 10 to the 10 per centimeter squared. So 10 to the 10 Q. So Q is just like, so this is 1.6 times 10 to the minus 19. Okay, so any questions? Yes, Josh. 10 to the 11. So I'm saying typically Q. Okay, in the industry, when we talk about a CMOS process, we mention what the fixed. We might mention what the fixed charge is, the oxide fixed charge is, and we always specify it in these units. It's 10 to the 11, 10 to the 10, or actually 10 to the 12 per centimeter squared. So what's implied is that it's 10 to the 11 charges per centimeter squared, or 10 to the 12 charges per centimeter squared. Okay, so that's a great question. Yes, so we're going to go over an example. So how do you know what this is? So this is dependent on the process, so on the fabrication process. So those of you who are taking EE130 have learned about thermal oxidation and the impact of annealing, the temperature and time and ambient on QF. But basically, this depends on the details of the fabrication process. Okay, so basically, the way we account for the impact of fixed charge, which is always present, is just to lump it into the flat band voltage. Okay, so this energy band diagram shows you the flat band. So this is, if I give you this energy band diagram, you should be able to tell me it's a flat band MOS band diagram. Okay? And that's because the definition of flat band is that the energy band diagram is flat in the silicon. Okay? Now, the reason why it's not also flat in the oxide is because of fixed charge or some charge at the interface. So qualitatively, if somebody were to show you this band diagram, you should be able to tell me, okay, there's charge, charge at the interface of this between the silicon and silicon dioxide, because there's an electric field existing when there's a flat band condition in the silicon. Okay, so remember, ideally, the flat band voltage is the built-in potential difference due to difference in gate work function and silicon work function. Okay, so that's still the case, but now we have to account for a fixed oxide charge. So this impact of the fixed charge on threshold voltage is just lumped into the flat band voltage term. So remember, VG is the flat band voltage plus the voltage dropped across the silicon plus the voltage dropped across the oxide. So this fixed charge is just going to affect the flat band voltage. Okay? Right. So now let's talk about, how do we measure it? Okay, so from last time we talked about the CV characteristic. And as I mentioned, during the manufacturing process, we can have simple MOS transistors, and we can, in the scribe lines that we destroyed later, but we just need to test them to make sure nothing went wrong in the process. So we can actually test simple MOS transistor structures as capacitors. So we just measure capacitance, gate capacitance versus voltage. So let's go over a simple example here. So let's assume this is an NMOS capacitor. So we're going to measure the gate capacitance as a function of the gate voltage. The CV curve is going to look something like this. Okay? So from a single measurement of a device during the manufacturing process, you can actually deduce multiple things. Well, first of all, you should know from the manufacturing process what is the material for the gate oxide and what is the material for the gate. So let's say, for example, we have polysilicon, N-type polysilicon, and we know somehow that the gate work function is 4.1 eV. So this is slightly different than the number I gave you for the homework, but maybe this band gap narrowing or something that increases the work function. But let's just say we know somehow that the gate material has a work function of 4.1 eV, and we know that the gate dielectric is silicon dioxide, and so therefore we know the relative permittivity. Now we don't know necessarily the thickness of the oxide. That's one thing that can easily change or vary in a manufacturing process. So the first thing we can do is we can look at the oxide. Let me just do this more neatly. We can look at the oxide, the maximum capacitance. Okay, so here's C max. Okay, so that's going to be equal to Cox. And so that's permittivity of the oxide, which we know from the material, over the thickness of the oxide. So you can, okay, so this is assuming you know the area of your transistor, which you design as a circuit designer or a process engineer, you actually draw the size of the transistor. So you know the size or the area of the gate. So once you measure the maximum capacitance, you know the, you can deduce the thickness of the oxide. Okay? Okay. That's the first thing. That's the first step. Okay, then from the minimum capacitance, we can determine the dopant concentration. Let's see. So what is this capacitance here? Let me just write the equation. C min equals 1 over Cox, which you already deduced, plus 1 over C depletion, the maximum depletion depth. Okay. Well, let me just write it out. So what is this depletion capacitance? Do you remember the formula again? It's permittivity of silicon divided by maximum depletion width. So that's the depletion width at threshold. Now remember the depletion width at threshold, let's write it up here, is the square root of 2 times epsilon silicon times the total voltage drop, so that's 2 times phi f, over Q times the dopant concentration. Right? Okay, now phi f is equal to kT over Q times the natural log of the dopant concentration over Ni. Okay, so the thing is, Wt is a function of the dopant concentration. Okay, so if you know C min, and you know C ox, and you know epsilon silicon, you just need to solve for Wt, and then that should give you Na. Yes, Lewis. Okay, so the good question, can you just tell from the flat band voltage? And the answer is no, only because in practice, the flat band voltage is not only given by this. Now for the homework that's due this week, yes, you can assume we're ignoring the oxide capacitance. So you can easily, yes, you can assume that the flat band voltage is equal to just the work function difference. But in reality, there's always going to be some fixed oxide charge. So in reality, we don't always know the fixed oxide charge. And something could have gone wrong in the process, so it could have like increased Q sub F. So this is why you have to use C min to figure out what the dopant concentration is, at least in the surface region of your silicon. Okay, so once we have this substrate doping N sub A, and we know the oxide capacitance, we can find the flat band capacitance C sub FB. So this is equal to, again, 1 over CFB is equal to 1 over C ox plus the silicon capacitance at the Debye capacitance, right? So this is the permittivity of silicon divided by the Debye length. Now the Debye length is a function of doping. That's why you had to find doping first. Okay, so then you find out what is the value of CFB, the flat band voltage capacitance. Then you can figure out, then you can see from the measurement what the flat band voltage is. Okay, this is step 3. Step 3 and step 4. Okay, then if you have the flat band voltage, then you can calculate F. Right. So you've basically deduced from what the flat band voltage is, you know the gate work function, you know the semiconductor work function because you know the dopant concentration, and you know the oxide capacitance. So then you can figure out what the fixed charge density is. Okay, so this way you can monitor your process to make sure that the oxide thickness is correct, that the dopant concentration is kind of correct, and you can also double check to make sure your threshold voltage is kind of what you expect for your transistors. And then you can see if there's something wrong with the quality of the gate oxide interface with silicon. Okay, any questions about, so an MOS capacitor CV measurement is very useful to just to learn as much as you can about the MOSFET fabrication process. Now, in reality, the work function of the gate is not always well known. So this is basically how you could also determine the work function of the gate material. So usually, so this is what you would do like with an experiment. Okay, it's not like in a CMOS chip manufacturing process that you can do this. Okay, so what is done is that usually you have to run a special experiment where you make capacitors of different oxide thicknesses. Okay, so you measure, so you make capacitors on the same wafer. So in other words, with the same gate material, okay, on the same dielectric, but just different dielectric thicknesses. And then what you can do is you can plot the measured flat band voltage as a function of the oxide thickness. Okay, so sorry, the terminology is a little bit different here, but T-ox, this is equivalent to what we've been calling X naught. Okay, so if we can actually conduct an experiment where we either with different wafers or on the same wafer somehow make the oxide thinner in some areas, and then deposit the same gate material everywhere to make all these capacitors with different oxide thicknesses, then we can, okay, so remember this is Cox is equal to permittivity of the silicon over X naught. So this term here is just the normal QF over Cox. Okay, so if you plot the flat band voltage versus the oxide thickness, the slope will give you what information? QF, right? And then the intercept will give you something. Well, if you extrapolate, okay, so which intercept are we talking about? So okay, so this is assuming, this is assuming that NA is known. Okay, so therefore, hence, phi s is known. Okay. So when X naught is 0, then the flat band voltage equals phi ms. So from the y-intercept, you find out what the gate work function is. Okay? Does that make sense? Okay, so these kinds of experiments were done like more than 10 years ago when the industry and researchers were trying to develop new gate stack materials for CMOS capacitors, CMOS transistors. So as I'll come back, okay, so the last part of today's lecture is about poly gate depletion. So polysilicon was the preferred gate material for many years because polysilicon actually can withstand very high process temperatures. Okay, so the way you normally make a MOSFET is you define the gate electrode, and then you form the source and drain regions in a self-aligned manner. So the source and drain regions are perfectly aligned to the edges of the gate. So you actually have a nice transistor formed this way. But to form the source drain regions, you have to blast the silicon with dopants, and then you have to anneal the silicon to heal the damage and get those dopants to reside on substitutional lattice sites. So that high temperature affects the gate material. And so doped polysilicon has no problem withstanding high process temperatures. Metallic gate materials do have problems. They tend to react with the oxide, the gate dielectric, if you subject them to high temperatures. So for that reason, silicon, heavily doped silicon was the preferred gate material. And it still is the preferred gate material for MOS transistors. But in recent years, as we've scaled the size of the transistors, we really have had to scale aggressively this oxide thickness. And as I'll explain later at the end of this lecture, people have really had to go to metal as the gate material. And so more than 10 years ago, people were starting to characterize, okay, what is the work function of various metal materials on various dielectric materials? Because once a material is in contact with a dielectric, it can have some charge transfer, and the effective work function might be different. So this kind of measurement was very common to look at all different kinds of metallic gate materials and all different kinds of high permittivity gate dielectrics to try to characterize, okay, what is the work function of this metal if we use it with this gate dielectric? Now, why do we care about the metal work function? Why is it so important? It basically determines the threshold voltage of your transistor. And that's a key parameter. In a couple of weeks, we'll cover that. The threshold voltage determines how well your transistor conducts current in the on state and how well it suppresses leakage current in the off state. So threshold voltage is very critical to control. The gate work function directly affects the threshold voltage, And so if you adopt new materials, it is really important to well control and well characterize your metal gate work function. So this technique was used, and if you read papers from like 10, 15 years ago, you'll see a lot of these kinds of measurements being reported. Okay, mobile oxide charge, ideally, in modern devices, is 0. Okay, but let me explain. So this is basically what happened, decades ago when people were trying to make the very first MOS devices. There's sodium, salt, in the oxides as in the MOS devices. So what would happen is that, well, over time, the threshold voltage would change, and maybe the threshold voltage was negative. Okay, so sodium is positive, so that would shift, tend to shift the CV curve all the way to the left, to very negative voltages. So you can't even, if you're trying to operate your transistor in this regime, plus or minus, a few volts, you don't even see anything happening, right? Because the surface is already inverted or depleted. Okay, so this plot on this curve just shows. Oh, okay. So what we do in manufacturing is that we actually do monitor how much contamination there is of, let's say, of sodium, some mobile ions like this. So the way this is done is we make MOS capacitors. Okay, so we just fabricate some simple MOS capacitors. And okay, looking at the CV curve, is it N-type or P-type substrate? N-type, good. So we make some simple capacitors, and we measure the CV curve. But we do two things. We first apply, where does it say? Okay, so we heat up the capacitor, and then we apply, let's say, a positive voltage. Okay, so I'm just circling this. So we apply a positive voltage on the gate, okay, so something much greater than 0, and we heat up this capacitor. And let's say there is mobile charge in the dielectric. Where will the mobile charge move? Will it be closer to the gate or closer to silicon? Silicon, that's right? So if the charge is mobile, it's going to be repelled by this positive gate voltage. So if you heat it up, you'll get all the sodium to diffuse down to the interface with silicon. Now, when it's down there, does it have more or less influence on the threshold voltage? More, right? So it shifts the threshold voltage more so to the left. Very good. Okay, so next, then what they do, so they take a CV measurement after a positive gate voltage on the MOS capacitor and heating it up. They take a CV measurement. Then they take it out of the measurement station, and then they apply, again, heat it up, but then apply a negative voltage to the gate. Okay, so if you apply a negative voltage to the gate, the charges will move up, okay, like away from, as far as possible from the silicon. So after negative bias temperature stress, there's a voltage bias and temperature stress, then the CV curve will shift to the right. I mean, right, the influence of that positive sodium is not going to be as much. So basically, the CV curve will shift to the right. Then, so basically, this is two extremes. All the sodium's at the top interface or all the sodium's at the bottom interface. And then they can actually look at the shift in flat band voltage between these two extreme cases. And that will tell them how much charge, how much sodium per unit area is, right? So this delta VFB will be equal to the mobile charge per unit area divided by the oxide capacitance. Okay? So this is just done as a process monitor, and ideally this delta VFB will be 0. And they just have to check it just to make sure that indeed, okay, nobody accidentally went to the lab and didn't follow protocol and contaminated the equipment. Yeah, okay. We actually do this in our research lab because sometimes people don't follow the rules. Have you experienced that in 143? So in our research lab, some people don't understand why you have to, wear gloves and things like that, and every once in a while equipment gets contaminated. The staff has to monitor to check and see if we need to clean the equipment. So we do this kind of measurement to make sure that equipment is actually not contaminated. Otherwise, researchers that are making advanced transistor structures, if they see some weird behavior, they won't know if it's because their device inherently has weird behavior or if there's something wrong with the equipment. Okay. All right, so this is the most difficult kind of oxide charge to understand. So let me try to explain it clearly here. Interface trap charge, or QIT, is dependent on the gate voltage. Okay, so the energy band diagrams on the right try to explain this. So let's say we're applying a large negative voltage to the gate. Okay, so that's on the left here of the energy band diagrams. So the surface is p-type. But that means that the Fermi level is actually close to the valence band edge. So if there are allowed energy levels at the oxide silicon interface due to dangling bonds, they will be mostly empty. Does that make sense? Right, because remember the Fermi level determines, okay, so most states below the Fermi level are filled, most states above the Fermi level are empty. Okay? So basically when you apply a bias, let's say large negative gate voltage, like over here in situation A, in regime A, basically the surface will be highly p-type, so most of the allowed energy levels in the band gap right at the interface will be empty. Okay, so let me see. Okay, so I didn't mention, so if you have a dangling bond defect at the silicon dioxide interface, that leaves, and that defect can trap charge, the energy of that charge associated with that trap is somewhere within the band gap. Okay, so that's what's represented here. We're just uniformly drawing some allowed energy levels in the band gap. Okay, but notice that those allowed energy levels only exist at the interface, right? Because that's the only place you have dangling bonds, like a high density of dangling bonds. In the silicon itself, you don't have, well, except due to occasional defects, you don't have these allowed energy states in the band gap of the silicon. So these are what we call localized energy states, allowed energy states. Okay, so now if we apply a more positive gate voltage or less negative voltage, we're going to start moving changing the band bending in the silicon. So the Fermi level, or to be more precise, the edges of the bands sort of shift with respect to the Fermi level. So as you apply more positive gate voltage, okay, as you increase VG in the positive direction, you'll start to occupy some of these states at the interface. So you'll change their charge state. So if they started out, in this particular example, if they started out positively charged, the ones below the Fermi level will be neutral. The ones above, which are still empty, will still be positively charged. But the net impact is that you're sort of adding negative charge to the interface. Right? So as you increase the gate voltage to the right, you're actually adding some negative charge at the interface. Okay, so let me just, if you add more positive charge to the gate, you have to have some negative charge showing up on the other side, right? That negative charge can come from changing the depletion width, or you can add holes in electrons, or you can add trapped charge at the interface. Okay, so ordinarily, when you increase the gate voltage, let's say if there are no trapped charges, ordinarily what would happen? In this case, this is also N-type silicon. So ordinarily, if you increase VG, what's going to happen in the surface of the silicon? This is N-type silicon. So if you put positive charge on the gate, what will happen? Well, okay, hold on. Let's say we started at large negative gate voltage. Okay, so at large negative gate voltage, which is A, we had a depletion, right? We had some depletion region. That's positive, right? Okay. So we formed a depletion region of certain depth, let's say W sub t. Okay, so as we make the gate less negative, what's going to happen ideally to that depletion width? They'll shrink, right? Because you don't need as much positive voltage. Yeah, if you increase the gate voltage, you'll have less positive voltage needed in the depletion region, right? So the depletion width will shrink. And so the capacitance, ideally, the capacitance will go up because eventually you'll start to add negative charge at the interface in the form of an accumulation layer of electrons. Okay, but if you're actually adding negative charge, okay, as you increase the gate voltage, rather than shrinking the depletion width, you're actually you're actually adding electrons to the interface. Then you're not going to change the depletion width as much as you normally would have, right? So the change in charge in the silicon is not coming from changing the depletion width, it's actually coming from trapping more electrons at the interface. So the depletion width will not change as quickly with gate voltage, and so that's basically what's shown here. Right, notice the depletion width is not changing as quickly with gate voltage because rather than having charge, changes in charge coming from the silicon bulk, it's actually coming from adding or subtracting charge at the interface. Okay, so one way of thinking about this is that, okay, as you're changing the gate voltage, you're changing the total amount of charge at the interface. So you can think of it as, well, it's kind of like QF, kind of like this, right? This, oops, where is it? Like here. It's kind of like, yeah, changing the charge at the interface. But the QF depends on the gate voltage, right? I mean, it's like the charge at the interface depends on the gate voltage. So that's kind of why I sketched all of these CV curves. Okay, so this is the ideal case, okay, if there's no interface traps. But because of interface traps, you have charge at the interface, so you're actually shifting the CV curve, but the amount of shift in the CV curve depends on the gate voltage. So it's kind of like, okay, at this gate voltage, you've shifted this CV curve this much. Okay, and then at this gate voltage, you shifted the CV curve like differently, and so on. Right? So basically, this CV curve, the stretched out CV curve is essentially, keep following the capacitance versus voltage curve, but with voltage dependent trapped charge at the interface. That makes sense? So basically, you can think of it two ways. You're not able to change the depletion or the form an accumulation layer as easily because now you also have another source of trapping or detrapping charge at the interface, right? So there's two ways to think about this. So whichever way is easier for you. The key is that the charge at the interface depends on the gate voltage, and the gate voltage influences, more precisely, it depends on the total band bending in the semiconductor, which is a function of the gate voltage. Okay? All right, so, but bottom line, what this means is that you need a larger change in gate voltage to change the surface from accumulation to inversion. Right? So you need to operate your MOS device with a larger supply voltage in order to change the surface from accumulation to inversion. Okay, so fundamentally, for like an integrated circuit, this means you have to operate your integrated circuit at higher voltage, and that's not desirable. Okay? So generally then, we'd like to minimize QIT, and again, this is done by performing certain steps during the fabrication process. So this plot here actually shows two curves. One with no hydrogen annealing of the MOS structure during the fabrication process, and another with hydrogen annealing. So hydrogen, if you heat it, if you subject silicon to this MOS structure to hydrogen gas at a high temperature, the hydrogen molecule will break up, and the hydrogen can end up bonding with silicon. So you can form SiH bonds at the oxide interface. So basically so if a hydrogen atom sort of satisfies the covalent covalently bonds with silicon, then there's no need to trap an electron there to fulfill that covalent bond. Okay, so basically you can reduce the interface trap density by what we call passivating these dangling bonds with hydrogen. In other words, they're no longer actively trapping and detrapping electrons. Okay, so ideally a hydrogen annealed MOS structure will have very, very small interface trap density, so it can be the closest to ideal. Okay, so VT is an important parameter to control in manufacturing because it determines how much current your transistor conducts. So during the manufacturing process, what we usually do is we fine-tune the threshold voltage depending on if we want a low power kind of a device. So for low power, we actually want high VT. I don't know why this is not working. Okay. So for low power, we want high VT. High VT. And for a high performance, we want low VT. So usually on a microprocessor chip or some system-on-chip integrated circuit, some parts of the circuit you want to operate at very high speeds, so high frequency. And other parts you just care about having low power consumption. And that means like in a memory, like SRAM, if you want to just store information, ones and zeros, you don't care to make very fast calculations, usually you want those transistors that are used for memory to have high threshold voltage, so they have low leakage current, off-state leakage current. For the critical paths on your integrated circuit, you want that limit the speed or throughput. You want low threshold voltage so that they have high on-state current, so the circuits can operate faster. So if you have more current in a transistor, you can charge and discharge capacitances faster. Okay. So on the same chip, then, how do you get transistors or MOS devices with different threshold voltages? Well, we can selectively add some dopants in different regions for different transistors and shift the threshold voltage. So this is what is done. Basically, let's say if you have an N-channel device, okay, so that's P-type substrate. If we want to increase the threshold voltage, that means, let's just do a simple example here. Here's an NMOS device, P-type silicon. Okay, so you can form an inversion layer by applying a gate voltage greater than the threshold voltage. Okay, so if you want to increase the threshold voltage, would you want to make the surface more P-type or less P-type? Well, if you want to make it harder to form an inversion layer. Yeah, more P-type. So you want to add more acceptor atoms. Okay? So notice that this simple formula, okay, Q times Ni, and Ni has units of number per centimeter squared. Okay, so this is the number of dopants you add per centimeter squared near the surface of your semiconductor. Okay, so Q, each donor or each acceptor will contribute one charge, Q. So that's why you have Q times Ni. So this basically will be some charge, coulombs per centimeter squared of the implanted dopants. Okay, and then we're assuming that all these implanted dopants are ideally located very close to the oxide interface, so they're located like right up against the gate oxide, ideally. So that's why this shift in threshold voltage can just be given by this simple equation. Okay, so Ni, if we define delta VT to be minus Q times Ni, and we know that delta VT is positive for acceptors, right? Like we add more boron and to increase the threshold voltage, then we know that Ni must be defined to be negative for acceptor atoms. And conversely, we know that if we made the surface of the silicon less P-type, that means we should add some donors. So Na minus Nd is smaller. So if we have to add donors, then we know that will decrease the threshold voltage, so it'll make it less P-type. Right? So delta VT is negative if you add donors. Okay? So in practice, this is how we adjust or fine-tune the threshold voltage. Okay, so the final topic, oh, not quite final topic, but almost, is gate depletion. Okay, so as I mentioned, because these are the polysilicon, heavily doped polycrystalline silicon thin films can withstand very high process temperatures, and that's why they were preferred for CMOS technologies for a few decades. Okay, but in reality, during the fabrication process, we really cannot dope it much more heavily than 10 to the 20 per centimeter cube. It's just practically not easy to do that. One reason is because the polycrystalline silicon is defective. It's not a single crystalline material, so there are lots of grain boundaries. At the grain boundaries, there are a lot of dangling bonds because, you know, the crystal structure doesn't line up properly, so you end up with some dangling bonds. And turns out that during the fabrication process, a lot of the dopants in the polycrystalline silicon actually segregate to the grain boundaries. And then, so they're not sitting in like a normal lattice site with, you know, 4 nearest neighbors, so they don't actually act as dopants. Okay, so there are a lot of this dopant. The number of dopants could be very high, but the number of active dopants that are contributing carriers is typically kind of low, depending on the polycrystalline, you know, defect density. But anyway, okay. So ideally, they're very heavily doped to be metallic, but in reality, as was already asked last week, in reality, they're not super heavily doped, so you actually could get depletion of the gate material, okay, if you apply a significant gate bias. So that's illustrated here. So now, assuming that the silicon is not perfect like a metal, that some band bending, some depletion can occur, resulting in some band bending. Okay, so this is an example for an NMOS capacitor. Right, so you have N plus polysilicon, to which you're applying a positive gate voltage over a P-type silicon semiconductor substrate. Okay, so yes, you apply a gate voltage to deplete the surface of the mobile majority carriers. So you have depletion region. You want to form an inversion layer to turn on, let's say, your transistor. But actually, not only do you have a voltage drop in the silicon and the oxide, but you also have a non-negligible voltage drop in the gate. Okay, so bottom line is then that the amount of gate voltage you need to apply in order to form an inversion layer in the silicon goes up. Okay, so threshold voltage essentially goes up. Okay, so oops, let's go back. Okay, so the question is, so what is the width of this depletion region? It's just given by the standard, you know, square root of 2 times the permittivity times the total voltage drop in the semiconductor, right? So this is the total voltage drop in the poly. So the width of the depletion region has to be, you know, given by this equation with V poly here as the voltage drop in the silicon. The dopant concentration in the polysilicon is in the denominator like that. Okay? Okay, so yeah, so basically this takes away from the inversion charge. Well, it reduces the inversion layer charge and actually degrades your transistor on-state current, simply because you're wasting a part of the voltage that you apply across the silicon gate. Okay, so the question is, how can you minimize this gate depletion effect? So there's 3 ways. Let's see if you can come up with at least a couple of them. Ah, very good. Heavy doping. Okay, so you can heavily dope the gate, but there are practical limits to that. So I think it's actually used in manufacturing. We researched this in the last decade. What we can do is take extreme measures to melt the gate. So there's laser, pulsed laser annealing, so you can have a nanosecond with, you know, time with pulse laser to just temporarily melt the silicon, and actually it turns out that way you can get a lot of the dopants residing eventually on substitutional lattice sites, so you can actually effectively increase the dopant concentration in the gate. So that's one way. What's another way? Use a metal gate. Okay, very good. But let's say that's it. And so Intel was the very first to use a metal gate material to get rid of the, one reason was to eliminate the polysilicon gate effect. But it took a long time for any companies to implement this. Oh, so they did this at the 45 nanometer generation of technology. So that was in the actually like 2007 or so, that they started using metal gate materials. So the reason why the metal gate material is very difficult to implement in manufacturing is because the metal gate material reacts with the gate oxide during high temperature processing. So before that, nobody had really solved that problem for manufacturing. And the way Intel solved it was that they formed polysilicon as the gate, then formed the source drain regions by implantation and high temperature annealing. Then they removed the polysilicon gate and filled the gap with metal. Okay, so they did, this is what we call the gate last process. This way, the metal gate never sees a high temperature process. And so people hadn't really thought about that as a viable manufacturing approach until Intel started to produce chips using that gate last process. Okay, there's another way to do this. You can dope the gate, in this case, p-type. Okay, so if you have p-type gate material, then, okay, so the reason why, let's see. So what kind of charge is in the gate in this case here, showing this energy band diagram? Is it positive or negative? The N-type silicon being depleted right at the surface. That's right. So it's positive charge right at this gate oxide interface. So another way to get that positive charge is just to make this N plus polysilicon gate p-type, so you'll get an accumulation layer, okay, at the surface rather than a depletion region. So the nice thing about an accumulation layer, so this accumulated, so this would be accumulated at the oxide interface. The nice thing about the accumulation layer is that it's, well, mobile holes, and the thickness of that mobile hole layer can be very thin. So you actually don't need to have much band bending in the gate to actually get that mobile charge in the at the interface with the oxide. Okay, so basically, if you use a p-type polysilicon gate, you can minimize the band bending in the gate. Okay. Okay, so we'll put it this way. So in order to drop let me think. Well, okay, so due to the, you have to keep the dielectric displacement continuous at this gate oxide interface. So you need to have some electric field in the silicon if there's electric field in the oxide. So you do need to have some charge, or yes, some charge density in the gate. So it just turns out that you can get that charge by depleting an N-type silicon, or you can get that charge by accumulating holes at the interface. And the holes are, yeah, basically if you have p-type silicon, you don't need to bend the bands. Right? So if you start with degenerately doped type silicon, you don't really need to bend the bands upward too much to accumulate, you know, significant number of holes at the interface there. So the voltage drop, the physical voltage drop in the gate can be essentially zero. Okay. Okay, so I just want to mention, so why don't people use p-type gate for an NMOS capacitor or an NMOS transistor? What would be the reason why we don't do that? Get rid of this effect. weaken the electric field? Well, it's a very simple reason. It has something to do with threshold voltage. If you use p-type polysilicon as the gate material rather than n-type polysilicon, what is that going to do qualitatively to your threshold voltage, your NMOS threshold voltage? Well, the work function of p-type silicon compared to n-type silicon much bigger. So what does that mean for your threshold voltage? It's going to be 1 volt higher. So generally, nobody wants to have a transistor with like over 1 volt, threshold voltage. So just practically, the threshold voltage is too high if you do this. Okay, so in recent years, only in recent years has this metal gate been a viable solution. But before that, many companies developed advanced processing thermal annealing techniques to really get as much dopant possible actively into the gate at the gate oxide interface. Okay, so the effect, as I mentioned, is to reduce the amount of voltage you can apply to the amount of band bending you can introduce into the silicon when you apply gate voltage. So we can actually just derive a simple equation for the, let's see, the effective, okay. So effectively then, when you're applying a gate voltage, you're going to get more voltage dropped across the combination of the depletion region in the poly and the oxide, gate oxide, versus the silicon itself, right? So usually when you're applying a gate voltage, you're trying to change the surface state of the silicon. So now you're going to lose more voltage across this dielectric. So you can think of this depletion region in the silicon as an extra dielectric layer that you're adding on top of the silicon dioxide. So effectively, you're thickening the dielectric thickness. But the permittivity of silicon is 3 times higher than oxide. So the impact is really the width of the depletion region in the poly gate divided by 3. Okay? So yeah, bottom line is the poly gate depletion effect, if it increases the effective gate oxide thickness by the width of the depletion region in the poly scaled by 3. Okay? Okay, so if we do a simple calculation, okay, so what is the width? Let's do a simple example. Let's say the oxide thickness is 2 nanometers. Okay, so usually the gate depletion effect is not of a concern unless your oxide thickness is really thin. Okay, so let's go through a simple example. So from Gauss's law, we know that dE dx is equal to charge density over, well, let's say in the polysilicon. Okay, but then this is equal to Q times the doping in the polysilicon, like this. So let's say we take let's integrate all of the charge. Let's do this. So we're going to integrate all the charge in the silicon, and then see what electric field that results in the oxide. Okay, in the polycrystalline silicon gate. Okay, so if we integrate all the charge in the polysilicon gate, that's Q times N poly times the width of the depletion region in the polysilicon. Is that right? Yeah, and that's, so if we integrate this Gauss's law equation, so this is going to give us the electric field sort of in the silicon, right at the oxide interface, right? So this is just from Gauss's law. But we know that the electric displacement has to be continuous across the gate and gate oxide interface. Okay, so basically, okay, just to summarize, we integrate Gauss's law. So all the charge in the polysilicon gate, that's going to result in some electric field, leaving the silicon gate. And we know that electric field in the silicon and the electric field in the gate oxide have to be related due to this keeping the dielectric displacement continuous. So anyway, so we end up with this equation shown here in the solution. And you can then derive that the width of the polysilicon gate depletion is on order of a nanometer. Okay, about one, maybe a little bit more than a nanometer. Now that's equivalent to a few angstroms. Okay, so as I mentioned, yeah, the gate depletion effect isn't really that big compared to depletion in the substrate. But if you're talking about gate oxide thicknesses that are approaching 1 nanometer, which is actually the case nowadays, the most advanced CMOS processes, the equivalent oxide thickness is about 1 nanometer. So even a few angstroms is going to make a big difference in your charge density, in inversion charge density eventually. Okay, so then you can see, okay, how much voltage is actually dropped in the silicon, in the gate. Okay, so this is assuming, in this particular example, we're assuming that we're dropping somehow, able to get 1 volt dropped across the gate oxide, across a 2 nanometer thick gate oxide. And that will give us electric field strength in the oxide. Okay, so how much then will there be voltage dropped in the polysilicon gate? It's 0.1 volts. So, you know, we're talking about 10%. You're losing 10% of the gate voltage that you apply across in the poly gate. And then the threshold voltage in this case, okay, in the simple case here, you have an extra voltage dropped across the polysilicon. So when you apply a gate voltage, okay, that equals the flat band voltage plus the voltage dropped across the silicon plus the voltage dropped across the oxide. Now you have an extra voltage drop across the poly. So then the threshold voltage is going to be higher by 0.11 volts. Okay, and that means that, well, you're going to have to operate your circuit at higher voltage, and that means more power consumption. Okay. Okay, that was a simple example. Okay, so then finally, the last non-ideality in an MOS capacitor that becomes important when you're talking about very thin oxides is inversion layer thickness. So when we actually form an inversion layer of mobile minority carriers in the silicon, okay, so this is a plot showing the oxide on the metal gate on the left, the oxide in the middle. Okay, so here's the gate oxide, and then now this is for VG greater than VT. We're forming an inversion layer. Okay, so in reality, the average distance of the inversion layer charge away from the oxide interface is greater than 0. So that's what's covered here in this last section. So it turns out then that the capacitance, okay, so when you change the voltage across an MOS capacitor, right, so we're applying a voltage across the capacitor. So if you add positive charge, oops, let's say we increase the gate voltage by a little bit, so we're adding a little bit of positive charge here. In inversion, we always were saying, okay, we're adding electrons at the oxide interface, right? So there's some depletion width and there's some depletion charge. But once we have a gate voltage higher than the threshold, beyond the threshold, we're adding electrons right at the interface. So the small signal capacitance is just going to be equal to the oxide capacitance because we're adding charge at both sides, both interfaces of the oxide. But it turns out that that inversion layer thickness is greater than 0. So in reality, we're adding the inversion layer charge. So as we are changing the gate voltage, we're actually adding the inversion layer charge a small distance away from the oxide interface. So the inversion layer capacitance, small signal capacitance, actually is going to be smaller than the gate oxide capacitance. So what this plot shows is, okay, this is for PMOS devices, and on the right, this is for NMOS devices. The scale you should look at is always to the left. Okay, so bottom line is, okay, here's 1 nanometer. 1 nanometer. Depending on the gate voltage, so this is a plot. Essentially, this is, I think this is proportional to effective vertical E field. So as you apply more and more, a larger and larger gate voltage, the voltage drop across the oxide will be larger. The electric field will be stronger. The vertical electric field will be stronger. So that will attract the mobile carriers closer and closer to the interface. So just look at, for if you increase the gate voltage to the right for NMOS or increase the gate voltage to invert more and more to the left for PMOS, basically the mobile inversion charge layer is going to be pulled closer to the dielectric interface. But bottom line is about 1 nanometer away. Okay, so the inversion layer thickness, just keep in mind, is on average is close to 1 nanometers when you turn on an NMOS device strongly. So capacitance in inversion, so once you reach the threshold voltage, as you increase the gate voltage more and more beyond the threshold, basically, wait, hold on. Okay, so here's the ideal. Red, okay, let me just draw this. So ideal would be this case here, right? This is what we covered last time. But in reality, the capacitance is, because of the thickness of the mobile charge layer, the capacitance will in reality never reach the ideal oxide capacitance. It'll be lower. Okay? So basically, the reason why you never reach COX is due to inversion layer thickness. And the reason why this small signal capacitance degrades as you increase more strongly in inversion is because of gate depletion. So remember, as you drop more and more voltage across the silicon, you'll get more and more voltage across the polysilicon gate as well. So the thickness of the depletion region in the gate increases. So that effectively increases your oxide thickness more and decreases your small signal capacitance. Yes, Louis? What is the slope? It would depend on the ratio of your real oxide thickness and the gate depletion width. You can actually calculate this, yes. But for this class, just qualitatively, just understand why in reality we never see the true oxide capacitance for a small signal measurement of an MOS capacitor. It's due to 2 things, but only one of those things depends so strongly on, like this, on gate depletion. Actually, let's just think about it. So last of all, if we plot CV, and it looks like this, how does this capacitance in inversion, as you go to, if you go further and further above the threshold voltage, how will that inversion layer capacitance, how will that inversion layer thickness affect, change? Will it get worse or get better? Well, okay, as you increase the gate voltage beyond the threshold voltage more and more, you're pulling the inversion layer closer and closer to the oxide because it's a stronger electric field attracting it to the oxide. Right, so the inversion layer thickness actually gets less as you increase the voltage. That's what's shown here. And so actually the inversion layer thickness effect is mitigated as you go to higher and higher threshold, higher and higher voltage above threshold. So the only thing that can explain this degrading capacitance with increasing voltage is the gate depletion. Okay, the inversion layer thickness phenomenon actually would go in the opposite direction. In fact, that's why this goes up over here. Because the accumulation layer is now getting pulled closer and closer to the oxide interface as you go to more and more negative voltage. Okay? Okay, if there are any questions, I'll answer them at the next lecture.